Tonight we slow down and look outward. A faint traveller has entered our skies, an interstellar wanderer named 3I Atlas, carrying dust, ice, and quiet mysteries. As it drifts past the sun, scientists listen closely to its light and hear a whisper of unexpected metals in its glow. Settle in. Breathe evenly. We'll follow the comet's gentle arc and let its story carry us toward rest. Imagine opening a planetarium app and watching a single pixel creep across the starfield. Wrong speed, wrong direction, wrong everything. That was the first whisper of the intruder astronomers now call 3I Atlas. The name looks like a riddle at first glance. The 3 marks it as the third known object from another star system to cut through ours. The I is how observers pronounce the Roman numeral I, and Atlas nods to the wide-angle sentinel that first noticed it. Behind the name sits a simple electrifying fact. This visitor does not belong to the Sun. Interstellar means exile. It means an object born in the cold outskirts of some other sun's nursery, tossed outward by the gravitational squabbles until it slipped forever from its home star's grip. Most of those vagabonds wander in darkness for ages. We almost never catch them. But every so often, geometry and luck align. The emptiness aims one straight through our neighbourhood. When that happens, the sky's quiet clockwork grows a little wild. The newcomer doesn't loop around like a comet or an asteroid. His path is hyperbolic. An open curve with an eccentricity greater than 1. Celestial shorthand for a one-way ticket. Gravity will bend it. The sun will heat it. Our telescopes will interrogate it. And then it will be gone. You can tell it's not local even before the chemistry enters the chat. The giveaway is motion. Local bodies, asteroids, comets, even most long-period drifters, share the solar system's general speed and plane, orbiting in elongated but ultimately closed tracks. 3I Atlas slashes across that order with a noticeable hyperbolic excess velocity, a leftover speed you can't erase with the sun's pull. Plot its position night by night and the scatter of points refuses to close. Fit a curve and you don't get an ellipse, you get an escape route. That's why the discovery sparked an instant scramble. Observatories around the world live for these unrepeatable alignments. If you miss your window, you don't reschedule. There is no later. Teams triggered target of opportunity programs, trading precious slices of telescope time for a gamble that this dim smear would tell us something about how other planetary systems build and break their worlds. Even amateur astronomers felt the ripple. The hunt for a faint dot moving against fixed stars is a game built on patience, skill, and a little stubborn joy. Step back and consider what it means to meet such a traveller at all. Our solar system is not a sealed snow globe. It leaks, objects get kicked out, and it also breathes in, occasionally catching wayfarers launched by other suns. 3I Atlas is a postcard from a different cosmic address, the kind you don't expect to find in your mailbox. It carries, frozen in its dust and ice, the conditions of another protoplanetary disk. The temperature gradient where it formed, the balance between rock and volatile ices, the trace elements that condensed when its natal star was young and loud and wrapped in gas. It is a sample return mission that launched itself. The dynamics are ruthless and beautiful. Picture a long, tilted approach, the body diving in from some steep angle relative to the ecliptic, the thin sheet where most planets orbit. As it falls sunward, solar radiation presses on its dust like a steady wind. Outgassing acts as a set of tiny thrusters, sometimes nudging the trajectory by millimeters per second in ways you have to model carefully to keep your predictions honest. At perihelion, the moment it brushes closest to the sun, the object brightens as any embedded ices wake up and rush into space. Dust lifts. Gas flashes into a transient atmosphere called a coma, and the newcomer paints a thin, glowing line across our detectors. Then momentum wins again, bending the path outward and away, the curve opening back to infinity. Names matter in stories, and they matter in science because they encode the path to discovery. Atlas isn't just a mythic titan holding up the sky. It's also the pair of robotic eyes scanning the heavens for anything that shouldn't be there. Earthbound guardians built to warn of asteroids but equally good at catching interstellar curveballs. The system's cameras are not romantic. They watch, they measure, they subtract last night's sky from tonight's, and whatever remains, whatever moves, gets flagged. The poetry arrives later, when people realise the flag is attached to a rock from somewhere else entirely. If you were standing on a dark hillside during one of its passes, you wouldn't see drama with your naked eyes. You'd see nothing at all, perhaps, or at best the faintest rise in brightness soaked by your retina and swallowed by city glow. That mismatch between the ordinariness of the visual experience and the enormity of what the thing is adds to the thrill. From a control room or a laptop miles away, spectra bloom. The faint light splits into lines that act like fingerprints telling us which atoms are present, which molecules are breaking apart in sunlight, how fast the gases are moving. Meanwhile, the orbit solution updates with every new position measurement, the data points collapsing uncertainty ellipses from somewhere out there to right here at this moment. Compare that for a moment with the two earlier interstellar celebrities. One slipped through like a whisper, more rock than ice, spooking everyone with its odd shape and non-gravitational push. The other behaved like a classic comet, flaunting its tail and announcing its ices in familiar tones. 3i Atlas arrives with its own personality, its own mix of speed, inclination, brightness, and outgassing, reminding us that interstellar object is not a single archetype, but a category as diverse as the disks that forge them. We are building a tiny census, one data point at a time, and every new entry widens the frame on how planets assemble from dust and gas. Even the geometry of observation carries meaning. When you look at a comet born here, you're peering into our family's pantry, water ice from our cold storage, organics baked and stirred by our sun. When you look at 3i Atlas, you're tasting someone else's kitchen. Was its home star hotter, flooding the disk with more ultraviolet radiation? Did giant planets migrate early and violently, flinging debris into deep space? Did it freeze in a reservoir richer in carbon dioxide, or cling to grains studded with metals? These aren't idle questions. The answers tie into whether life-friendly ingredients are common, whether disks tend to make rocky worlds like ours, and how often systems self-edit by ejecting the leftovers. The chase is also a technical showcase. You need fast scheduling to catch it near perihelion. You need sensitive spectrographs to tease out lines from a target that's both faint and fading, instruments that can lock onto a moving point and track it smoothly across the slit. You need careful subtraction of Earth's own atmospheric signatures. You need coordinated coverage, ultraviolet from orbit, infrared to chase hidden ices, radio dishes to sniff out big slow-turning molecules, and nimble backyard telescopes to fill gaps the giants miss when sunrise ends their night. If there's a human feeling that threads through all this, it's the strange intimacy of distance. 3i Atlas is unimaginably far and immeasurably alien, yet it obeys the same physics that governs a tossed set of keys. It is anonymous, no mythology attaches to its original sun, but it is readable. We draw lines through time and space, we fit curves, we infer. The object knows nothing of our curiosity. It is only doing what gravity and sunlight demand. Still, for a few weeks or months, it becomes a character in our story, a mirror we hold up to our models of how worlds cohere and come apart. There is too the quiet awareness that this is practice for the next one. Detection networks are improving, survey telescopes are getting wider, deeper, faster. Each interstellar encounter teaches us what to prioritise when the alert pings at 3 AM, which filters to slot in first, which exposure times to gamble on, how to coordinate across continents. You can't rehearse a unique event, but you can learn the reflexes that make your first glance count. And as the newcomer angles closer to sunlight, ticking along its open curve, our instruments keep watching. Positions penciled down with deliberate care, spectra stacked, Models updated in the background of a planet that spins and cities that sleep, while a small cold messenger from elsewhere skims past the furnace at the centre of our sky. The night shift at Rio Hurtado begins like most others, a 0.5 metre telescope with a 7+ degree field of view, slews, settles and drinks in a 30-second exposure of the southern sky. Then it does it again, and again, and again. Atlas's rhythm is 4 passes on the same patch of sky about 15 minutes apart. Just enough spacing that anything moving will betray itself while most stars stay put. The software subtracts tonight's frame from a deep reference image, looking for new points of light. Cosmic rays, hot pixels, airplane glints, those get thrown out by learned reflex. What remains are the candidates sorted by a real bogus score and bundled into tiny time-stamped sequences called tracklets. On most nights that's the vocabulary of nearby asteroids. On this night one tracklet doesn't fit the grammar. In the control logs it begins as a dim, slightly trailed smudge just above the noise floor. The Chill Station, Observatory Code W68, has been making sky movies like this since it came online, scanning the south with the same metronomic cadence as its siblings in Hawaii and South Africa. The pipeline links the 4 detections, measures the apparent rate and direction, and flags an object whose motion is too fast for a distant slowpoke, yet too coherent for a glitch. The flag isn't alarmist, it's a nudge to human eyes. Look here, someone does. The centroids are clean, the point spread looks real, and the motion is consistent across the quartet of exposures. Before anyone slaps on a grand name, there's the ritual. Post the measurements to the minor planet center, solicit follow-up, extend the arc. Within hours and then days, additional positions tighten the orbit from guesswork to geometry. The timestamps are July 1st and 2nd, 2025, and the place is Atlas CHL at El Sos Observatory in Rio Hurtado, Chile. Provisional designation C/2025N1 Atlas. The early fit refuses to curve into an ellipse. Eccentricity lands greater than 1, interstellar. The Chile discovery post that started as one more nightly anomaly blossoms into a global target of opportunity. How can a small survey camera be so sure so fast? It isn't magic, it's the cadence. Atlas is built to sweep the entire visible sky several times per night down to about 19th magnitude, favouring speed and coverage over depth. 4 exposures per field let the software connect dots into motion, reject imposters, and spit out a first draft orbit good enough for other telescopes to pounce. By design, that's planetary defence DNA, find fast movers headed our way, but it turns out to be perfect for catching visitors from away as well. When the motion and the skyplane angle are just so, hyperbolic solutions pop out early. The NASA write-up that follows a few days later includes a simple animation of the discovery images. A fuzz that walks across a static sea of stars. There's no soundtrack, no dramatic zoom, just the quiet insistence of motion. Alongside the clip is the key line, the NAS A funded A TLAS. Telescope in Chile first reported that this object originated from interstellar space. In other words, from the very first frames, the path itself was the message. Once the word interstellar is whispered with confidence, the cavalry assembles. Larger apertures queue up for deeper exposures. Spectrographs align slits to catch whatever gases the newcomer exhales. Hubble trains its optics on the fuzz by July 21st, capturing a teardrop coma that validates what the survey camera implied. There's a real active body here, not a trick of subtraction. But all of that is follow-through. The catch, the moment of capture, belongs to the small, fast machine in Chile that noticed a minnow bright point sliding in the wrong direction at the wrong speed. From the very beginning, the southern vantage mattered. 3i Atlas arrived from low in the sky for northern observers, out of the crowded starfields near Sagittarius. With the Chile station watching, the object's early arc was longer, cleaner, easier to fit. That geometry, plus Atlas's cross-hemisphere design, is exactly why the network was expanded. Wider latitude means fewer blind spots, more parallax leverage, and more nights where weather at one site doesn't end the movie. Even the raw mechanics of the find tell a story. The discovery frames show the familiar. Stars as points, the comet as a point too, but a point that won't sit still. The centroid positions get fed to orbit solvers. The solver returns a hyperbolic excess velocity you can't get from any gravitational slingshot inside the Sun's family. That number is not poetry, it's a threshold. Cross it, and your past light cone doesn't intersect the birthplaces we know. Cross it, and a survey camera's routine night becomes page 1 of a very different logbook. The next nights look similar from the outside: slew, expose, subtract, score, send. But now the pieces drop into place with a sharper click. The same code that rejects airplanes and cosmic rays is now feeding the world with the precise, time-tagged breadcrumbs needed to steer giant mirrors and space telescopes. The Chile station keeps pressing its advantage: clear winter air, southern declinations, deep reference stacks, while sister sites thread coverage through their own nights, and the queue of follow-ups grows longer than the sky can hold at once. Somewhere in that flow, the cadence of 4 images, the subtraction scars, the line of centroids marching pixel by pixel, 3i Atlas stops being a rumour in a database and becomes a track you can feel in your fingertips. A new object moving with a purpose that isn't ours. The kind of motion that teaches a small survey scope on a cold hillside how to change the questions everyone else will ask before dawn. The first hint wasn't a picture. It was a barcode of light. Take the glow around 3i Atlas, smear it through a spectrograph's prism, and you don't get a rainbow. You get knife-thin lines at precise wavelengths. That barcode said something that makes comet scientists sit forward. Among the familiar molecular bands, razor-bright atomic nickel lines were flickering in the near UV/blue part of the spectrum. Metals, in a coma, from an object that started life around another star. On a cold, impeccably steady night, teams on the European Southern Observatory's Very Large Telescope reached for 2 workhorses: UVES, a high-resolution optical spectrograph, and X-Shooter, a wideband spectrograph. They subtracted the dust continuum, hunted for narrow spikes, and the pattern popped, a comb of Ni transitions, with especially strong features near 3,414.8 angstroms and 3,524.5 angstroms. It wasn't a one-off blink. Repeated visits showed the same atomic signature, and something just as striking by its absence. No FEI. Lines to comparable limits. Nickel, yes. Iron, number. For a comet, that's weird. For an interstellar comet, it's riveting. Dates matter in a chase like this. The VLT team reports the strongest nickel lines on July 20th, 2025, when 3i Atlas was still far from the Sun, near 3.9 astronomical units. CN, the cyanide band that usually lights up early in normal comets, didn't show until August 14th to 15th at approximately 3.1 astronomical units. The order of appearance flips the usual expectation: metals first, CN later. The authors quantify the outflow too. By August 21st, at 2.85 astronomical units, they derive production rates around log QCN approximately 23.6 seconds to the power of -1, and log QNI approximately 22.7 seconds to the power of -1, with Phi still undetected. That combination points to a release pathway for nickel that turns on at lower temperatures than the molecules feeding CN. Why would nickel atoms pour into space while iron stays locked up? The spectra argue against just heat the rock. If you simply warmed classic metal/sulfide grains, the activation barriers are too high at these distances. Instead, the data point to low-energy release mechanisms that can operate in a cold coma. Photon-stimulated desorption from dust, UV sputtering, or the photolysis of volatile metal-bearing molecules that are far easier to break apart than refractory crystals. One leading candidate is nickel carbonyl, NiCO4, a molecule that forms when neutral nickel binds to carbon monoxide at modest temperatures and then snaps apart under UV light to yield free nickel atoms. It's fragile, it's efficient, and crucially, NiCO4 is more robust than FeCO5 in water-rich, mildly oxidizing conditions, naturally producing nickel without much iron. The VLT team even predicts that if this carbonyl route dominates, nickel brightness should track CO or CO2 outgassing more strongly than it tracks water. Almost on cue, space telescopes chimed in with the other half of the chemistry. JWST took a long look and saw a CO2-dominated coma, one of the highest CO2-H2O ratios ever measured in any comet, roughly 8:1 at 3.32 astronomical units inbound. Spherex followed with multispectral maps, confirming abundant CO2 and water ice. Those results dovetail with the carbonyl picture, a CO/CO2-rich environment feeding a nickel carbonyl pathway that lights up before the classic water-driven chemistry takes over. This is not the first time nickel has shown up where conventional wisdom said it shouldn't. In 2021, astronomers reported neutral nickel and iron atoms in the comae of many solar system comets and in the interstellar Visitor 2I/Borisov, establishing that metals can leak into the gas phase even far from the Sun. 3I Atlas, though, is carving out its own profile. Ni without Fe to current limits, Ni appearing before CN, and Ni intensifying steeply as the comet infalls. Together, those differences sketch a different kind of surface chemistry and a different temperature ladder for turning solids into gas. Under the hood, the measurement is a minor marvel. You start by flattening the red slope dust continuum around approximately 21 to 22% per 1000 angstroms in the optical. Then you fit Gaussian profiles to each candidate nickel line and compare the observed intensities to a multi-level fluorescence model that accounts for the solar spectrum pumping those atoms. That lets you convert line fluxes into column densities and then into production rates, apples to apples across nights as the heliocentric distance changes. Do the same trick for CN's 3880 angstrom band and you can watch different chemistries turn on at different radii from the Sun. The upshot, you can literally plot the comet's chemistry versus sunlight. What would nickel look like in the coma if NiCO4 is the parent? It should be tight to the nucleus. With a short parent lifetime, photons shred the carbonyl on very short timescales, creating a steep central spike in nickel density, with only modest extension into the tail. If dust jets inject fresh nickel-bearing grains into CO-rich streams, you might even see anisotropic nickel jets in high-resolution maps. And if the carbonyl path is right, nickel flux ought to correlate with CO2 rather than with water. A fingerprint JWST or SPHEREX can test as the geometry evolves. There's a broader comparative lesson here. In 2I/Borisov, CN and the metal lines arrived closer to the Sun and in a different sequence. In many native comets, CN is a familiar early riser. 3I Atlas has flipped that script. The sequence may speak to how and where the object formed in its natal disk, perhaps near a CO2 ice line, perhaps in radiation-processed ices that store oddball carbonyls and metallated organics, then got ejected into interstellar exile. The CO2 richness pushes the same way. Either the nucleus is intrinsically CO2 heavy, or heat struggles to penetrate, suppressing water relative to CO2 and CO at large distances. Both pictures favour nickel-friendly pathways. If you like your mysteries quantified, look at the Ni/Fe constraint. Solar system comets often show nickel and iron in comparable ballparks once you factor in fluorescence efficiencies. Here, iron is below detection while nickel is robust, which could mean iron carbonyls are being quenched by hydrolysis oxidants where NiCO4 survives. 2. Redox partitioning in primitive grains leaves accessible nickel metal or Ni-rich nanophases, while iron is tied up in more resistant minerals. Or 3. We're seeing observational bias, and Phi will emerge as activity ramps up. Each scenario has a different prediction for how the spectrum should morph as 3I Atlas warms, and so the nightly ritual continues. Continuum off, lines on, models updated. As 3I Atlas drops sunward, observe as a stacking spectra to watch nickel lines thicken and sharpen, cross-checking against CO2 light curves from space and hunting for the first clean whiff of iron. Somewhere in the thicket of numbers, production rates, fluorescence fits, heliocentric scalings, is the precise chain of events that frees metal atoms into the mist. You can feel the chemistry change as soon as sunlight starts to bite. At a chilly 3.3 astronomical units from the sun, far beyond where most comets put on their best water show, the coma around 3I Atlas didn't smell like steam at all. It smelled like carbon dioxide. Webb's NIR spec peeled back the glow and found the unmistakable 4.26 micrometer spectral hill of CO2 towering over the 2.7 micrometer water band, with CO2 outgassing 8 times stronger than H2O at that distance. That 8 plus or minus 1 ratio isn't just high, it's among the highest ever measured for any comet, and 6 sigma above what you'd expect from solar system regulars at the same heliocentric range. The observation came early on August 6, 2025, when NERSPEC scanned from 0.6 to 5.3 micrometers and mapped the coma in gas and dust. The CO2 didn't just dominate, it leaned sunward, forming a lopsided plume that told a simple story. The daytime hemisphere was doing the heavy lifting. In the same spectral cubes, Webb also picked up water ice grains, gas phase H2O, CO, and a whiff of OCS, but all of them rode in CO2's wake. CO2 is a colder trigger than water. At 3 plus AU, the nucleus surface can sit near approximately 150 Kelvin. That's unfriendly to vigorous H2O sublimation, but perfect terrain for CO2 to lift off. So instead of a water-powered geyser, 3I Atlas behaves like a dry ice engine. Sunlight loosens CO2 from shallow layers, it rushes out, drags dust with it, and builds an atmosphere whose chemistry is upside down compared to most comets we've met nearby. Webb's team folded those spectra into production rate models and landed on the striking conclusion. Either this nucleus is intrinsically CO2 rich, or heat cannot penetrate deeply enough to free much water at these distances. An insulating crust can starve H2O while CO2 vents from nearer the surface. A second set of eyes helped trace the plume's reach. Sphere X, launched in March 2025 to map the sky in 102 near-IR colours, watched 3I Atlas soon after Webb and reported an extended CO2 coma, a fat halo that stays bright well beyond the nucleus, consistent with sustained CO2 release rather than a brief burp. Sphere X's wide-field multi-band maps aren't as sharp as Webb's, but they're perfect for seeing how far the carbon dioxide glow spreads and how it waxes as the sun angle changes. If you put those pieces on a whiteboard, CO2 towering over H2O at RH equals 3.32 AU, a sun-facing jet and an expansive CO2 halo, you start circling 2 formation scenarios. 1. 3I Atlas was built near a CO2 ice line in its home disk, where carbon dioxide froze out efficiently, loading the nucleus with volatile dry ice. 2. It formed in or drifted through a radiation-rich environment that altered near-surface chemistry, stockpiling CO2 and other carbon-bearing volatiles in layers that are easy to desorb when the first sunlight hits. Webb's analysis leans toward an intrinsically CO2-rich nucleus, with the caveat that poor thermal diffusion, a crust that keeps heat out, would also suppress water relative to CO2 and CO at large distances. Both effects can cooperate. The maps themselves are unusually expressive. In NIR Spec's flux images, the SAT-YO2 at 4.3 micrometers paints a bright, compact core with a fan-shaped apron into the day side. H2O at 2.7 micrometers appears fainter and tighter. Dust near 1.2 micrometers outlines an asymmetric coma that tracks the same sunward thrust. That geometry suggests discrete active patches on the nucleus feeding CO2 jets, with dust loading that changes minute by minute as the source rotates through daylight. Chemically, 3I Atlas refuses to be a twin of anything we've studied up close. Yes, the outlier C/2016 R2 had strange carbon chemistry, but most long-period and Jupiter family comets fall along a predictable CO2/H2O trend with distance. 3I Atlas sits far above that fit. In the web data, CO/H2O looks less extreme than CO2/H2O, which hints that CO2, not CO, is the principal early driver. That skew matters for dust dynamics. CO2's momentum transfer can lift larger grains than a feeble water flow at the same temperature, reshaping the coma's texture and how quickly sunlight reddens it. Down on the optical side, spectroscopists on big ground-based mirrors have been sniffing the gas zoo and comparing timelines. A curious pattern emerged in August. CN, a classic tracer band, lit up after the CO2 dominance was already clear, while a forest of neutral nickel lines appeared even before CN came on strongly, an inversion of the usual order that points to low-energy release routes operating in a CO/CO2-rich flow. If nickel really tracks carbon oxide outgassing through fragile carrier molecules like carbonyls that are easy to photolyze, then the CO2 light curve isn't just a coma metric, it's a metal release metronome. From a practical standpoint, a CO2-led coma changes how you chase the object. Instruments tuned to 4.3 micrometers carry extra weight. Exposure times and slit orientations get optimized for that sunward lobe, and coordinated campaigns pair space-based infrared for CO2 with optical/near UV for N and metal lines to watch which species surge as the heliocentric distance falls from 3-something AU toward the low 2s. With every new spectrum, the CO2 peak breathes, the dust fan reshapes, and the gas ratios inch along a curve that refuses to look ordinary. You don't need to touch a comet to know what it's made of, you just have to catch its light misbehaving. Take the faint glow around 3I Atlas. Let a spectrograph spread that glow into thousands of razor-thin wavelengths, and look for lines that are too bright or too dark compared to a smooth rainbow. Each element and molecule stamps a few very particular lines. Together they form a barcode you can read from millions of kilometers away. The dance starts long before the photons hit the detector. A telescope locks onto a target that isn't moving like the stars. It's drifting across the sky, so the mount tracks the comet's non-sidereal motion to keep the slit centered. In instruments like UVES or X-shooter on the Very Large Telescope, you pick a slit width that balances signal against spectral sharpness. A narrower slit means higher resolution. Individual lines separate cleanly instead of blurring, but you lose light, and comets are stingy with photons. The detector then stacks a series of exposures while the comet and Earth both move. Between exposures, observers nod and dither the slit to help subtract the sky's own glow. Raw frames are just the prologue. Calibration lamps, thorium-argon, laser combs, or both, pin down the exact wavelength scale so a bump at 3,414.8 angstroms is truly where you think it is. Flat fields smooth out pixel quirks. Standard stars put the spectrum onto a physical flux scale. Then comes telluric correction, stripping away the fingerprints of Earth's atmosphere, oxygen, water vapor, CO2, that otherwise masquerade as comet chemistry. Only after that do you get the clean one-dimensional spectrum you can interrogate for metal lines, molecular bands, and forbidden oxygen glows. Atoms in a comet's coma don't shine because they're hot like a light bulb. They shine because they're being pumped by the sun. Solar photons hit an atom, kick an electron up, and when it falls back, the atom re-emits at exactly the element's allowed wavelengths. That's resonance fluorescence. And it sets a predictable conversion between sunlight and line brightness called a G-Zu factor. The trick is that these G-factors aren't constant. As a comet speeds toward or away from the sun, the solar Fraunhofer lines slide across the atom's absorption lines, the swings effect, turning some lines on and others down. High-resolution spectra let you model that pumping precisely. Once you do, the line intensity turns into an actual column density of that atom along your line of sight. And with a simple coma model, think Hazer or vectorial, you can back out a production rate. Metals were once thought to be passengers locked in dust, released only when grains were roasted near the sun. That story cracked in 2021 when high-resolution spectra showed neutral nickel and iron atoms drifting in the cold coma of ordinary comets, and even in the interstellar visitor 2I/Borisov, far from any furnace that could boil metal sulfides. That discovery forced everyone to consider low-temperature release paths, UV sputtering off grains, photon-stimulated desorption, or fragile metal-bearing molecules that shatter in sunlight. With 3I Atlas, the metal smell is unmistakable. Teams using VLT's UV as an X-shooter pulled out a forest of Ni lines, classic nickel transitions, while Thai stayed invisible to deep limits. Even more provocative, the nickel lines brightened dramatically at large heliocentric distances before some of the usual carbon radicals like CN had fully come up, pointing straight at a low-energy release mechanism rather than hot sublimation from rock. The authors show how the Ni lines can be fit with a fluorescence model to yield production rates and argue that the behaviour is inconsistent with baking metal grains. Instead, it's consistent with nickel atoms emerging from fragile carriers, for example nickel carbonyl NiCO4, that form in CO/CO2 rich environments and photolise easily under sunlight. In that picture, nickel should track CO or CO2 outgassing more than it tracks water. Reading those nickel lines requires careful work at the angstrom level. You start by removing the sloped dust continuum. Comet dust reddens the spectrum, so the gas lines stand on a flat baseline. Each candidate Ni line is measured with a Gaussian or Voigt profile. Blended lines are deconvolved, and dubious features are rejected if they don't share the same Doppler shift, or if they vanish when you rotate the slit, a tell that they were residual sky features. What survives is matched to atomic databases to confirm term designations and transition probabilities. The line set must be self-consistent across multiple nights and a range of comet-sun velocities, otherwise you've fooled yourself with noise. Because Phi and Ni both fluoresce, you can compare their production rate ratio once you correct for different G factors. In many solar system comets that show both metals, the ratio lands in a familiar ballpark. In 3I Atlas, nickel dominates while iron is undetected, a chemical asymmetry you almost never see if both metals came from the same refractory reservoir. That asymmetry is exactly what a carbonyl pathway would predict. NiCO4 forms and survives under conditions that quench FeCO5, so sunlight frees Ni atoms while Fe stays locked up. It's an elegant way to get a bright Ni signal at low temperatures and large distances. No blowtorch required. If you want to turn line brightness into geography, you trade a single spectrum for spectral mapping. Step the slit across the coma or use an integral field unit, and you can draw a nickel abundance map. A sharp peak near the nucleus if the parent molecule dies fast, or a broader glow if the parent lives longer. Pair that with a dust continuum map and with infrared maps of CO2 at 4.26 micrometers, and you can test whether the metal really hugs the CO2 jets. With 2I/Borisov, such comparisons helped prove metals weren't a fluke. With 3I Atlas, early results already hint at the same low-temperature chemistry playing out under CO2-dominated conditions, just with a twist in the Ni versus Fe balance. The arithmetic that connects a handful of photons to "there is nickel here" is surprisingly unforgiving. You propagate uncertainties from flat field noise all the way to the final log Q of Ni. Fold in the comet's expansion speed, inferred from line widths or assumed from empirical scaling, and check that different Ni lines give the same answer once you account for their pumping strengths. You also model photoionization lifetimes. Neutral nickel doesn't stay neutral forever, and correct for the fraction of atoms kicked into Ni+ before they can fluoresce at the observed wavelengths. Only then can you compare nights fairly as the comet's distance and phase angle change. All of this is why the phrase "we smelled metal" means something very specific. A reproducible, instrument-calibrated, sky-subtracted, Doppler-aware sequence of steps that turn starlight into elemental fingerprints. And it's why a spectrum that shows night eye up, fear eye down under a CO2-rich coma doesn't just read like trivia, it reads like a process memo from the surface of an interstellar nucleus, written in lines so narrow you could slide a hair through them. Nickel is supposed to be the quiet, stubborn stuff, locked in rock, welded inside sulfide grains, too refractory to turn into gas unless a comet is practically skimming the sun. For decades that was the story. If you wanted free metal atoms, you needed hellish heat. Then high-resolution spectroscopy began turning up nickel and iron vapor in cold comae, a shock that rewrote expectations and made astronomers wonder what low-temperature trick was prying metals out of dust. Against that backdrop, what's happening around 3I Atlas is not just surprising, it's diagnostic. Start with the observation that tilted the field, a forest of neutral nickel lines in the blue optical, measured repeatedly with big telescopes, while iron stayed invisible to very deep limits at similar distances from the sun. If metals were simply cooking out of the same mineral grains, you would expect Ni and Fe to rise, or hide, together. They didn't. The spectra show nickel lighting up early and hard as 3I Atlas moved from roughly 4.4 to 2.85 astronomical units, with FAY remaining undetected in those same datasets. That asymmetry is the clue something is selectively freeing nickel. Even the way nickel ramps up is odd. The measured production rate of Ni increases extremely steeply as the sunlight strengthens, much steeper than you'd get from simple warm the rock, boil the metal intuition. In fact, the VLT team fits a power law close to Q of Ni proportional to ERH to the power of -8 over that inbound stretch, which are far more aggressive than classic water or dust-controlled scalings and points to a low activation energy release that becomes wildly efficient once the right photons are available. Fe should be along for the ride if it shared that parent process. Its Senno tells you the parent reservoir for nickel is chemically distinct. That's where chemistry does its mischief. One pathway that matches both the early turn-on and the Ni greater than Fe imbalance is the formation and breakup of nickel carbonyl, NiCO4. In cold, carbon oxide-rich environments, stray Ni atoms, or Ni sitting at the surface of grains, can coordinate with CO to build NiCO4, a volatile, fragile complex that desorbs easily and then photolizes under sunlight into free nickel atoms, plus carbon monoxide fragments. Its iron cousin FeCO5 is fussier. It forms and survives under a narrower set of conditions, and is more easily quenched by water and oxidants. Result, you get lots of nickel atoms without comparable iron at the same time and place. That's exactly the signature the spectra around 3I Atlas are sketching out. And it naturally predicts that nickel brightness should track carbon oxide outgassing rather than water vapour. Independent lines of evidence backstop the carbonyl idea. When JWST peeled open the infrared, it found the coma dominated by CO2 at a heliocentric distance of 3.32 astronomical units, with a CO2/H2O mixing ratio approximately 7.6 to 8 to 1 and a sunward-leaning jet, conditions tailor-made for building and then shattering nickel carbonyls. In other words, the gas bath around 3I Atlas is exactly the kind of carbon oxide-rich environment that favours Ni pathways at temperatures where water-driven chemistry is still sluggish. The timing matters too. In solar system comets, A familiar sequence is that CN from HCN or related parents pops up as activity grows and water wakes. At 3i Atlas, observers report nickel arriving conspicuously before CN strengthens, with CN lines only becoming clear as the comet pushes inside approximately 3 astronomical units. That reversal of the usual order is another hint that a CO/CO2 tuned mechanism is leading the dance, and that nickel has a different thermostat than the standard radicals. It's not that 3i Atlas lacks the usual molecules, it's that metals are getting an early low temperature on-ramp that iron, for chemical reasons, can't use as efficiently. Why is this so startling, given we already learned in 2021 that metals can appear far from the sun? Because those earlier detections typically showed iron and nickel together, often in comparable ballparks once you correct for fluorescence physics. The 3i Atlas spectra don't do that. They privilege Ni, forcing a more specific story about the parent reservoir and its surface chemistry. Instead of a generic metals can leak off dust, we're seeing selective release keyed to carbon oxide chemistry and to the redox environment of the grains and ices, which may differ sharply from the stuff we're used to in our own comet families. There are other plausible, non-exclusive contributors, each with a different fingerprint. Photon-stimulated desorption can shake atoms off grain surfaces without heat. UV sputtering can ablate the outermost layers of dust. Mild thermolysis can crack metal bearing organics or Ni-rich nanophasers baked into Theus regolith. But these mechanisms don't automatically explain why iron lags while nickel surges. The carbonyl route does, especially when paired with CO2-led activity, and a crust that insulates water at large distances, so H2O stays muted, while CO2 and CO carry the momentum. The spectra essentially invite you to read Ni as a proxy for the carbon oxide circuit powering the coma at this stage. On the nucleus itself, the asymmetry hints at natal heritage. A body that formed near a CO2 ice line in its home protoplanetary disk, or that marinated in hard radiation before ejection, could store layers where carbon oxides and metal atoms readily couple on cold surfaces. Eons later, a modest dose of sunlight in our sky would be enough to start low-energy chemistry that prefers nickel, long before deep heating wakes the water-driven suite that tends to bring iron along. If that picture is right, 3i Atlas isn't simply weird, it's a chemical storyteller, carrying a surface prepared in a different disk with different UV fields and dust redox states. Observationally, the testable predictions are straightforward. If NiCO4 is doing the heavy lifting, maps of the coma should show nickel abundance peaking tightly near the nucleus, short parent lifetime, and covarying with CO2 brightness across the sunward jets. As the comet falls inward, iron lines might wake later, once higher temperatures, deeper cracks, or different parents begin to contribute. The VLT team explicitly predicts a Ni-CO2 correlation, and reports the FE non-detections across the early arc, giving observers a clean checklist for the next weeks of spectra as the heliocentric distance continues to drop. And so nickel, once assumed to be a mute passenger, has become the loudest voice in the room, a set of razor-thin lines that rise too fast, appear too early, and stand alone without iron, all in a coma where carbon dioxide is in charge. Every fresh exposure adds another sliver of that voice to the stack, the profile of each knee line sharpening as 3i Atlas rotates and the sun angle changes, the story written in fluorescence and distance and the stubborn chemistry of cold light. If you lay the 3 interstellar visitors side by side, Oumuamua, Borisov and 3i Atlas, you can feel how each one stretched a different muscle in planetary science. The first, 1I/Oumuamua, never grew a visible coma and still managed to veer off a purely gravitational path. The second, 2I/Borisov, behaved like a textbook comet but with a chemical accent. The third arrives wreathed in gas that doesn't match our usual playbook for activity at its distance. The scoreboard isn't about winners, it's about what each object lets us measure that we couldn't before. Start with the oddball that opened the door. Oumuamua looked inert in images, no tail, no fuzzy coma, and yet its trajectory carried a detectable non-gravitational acceleration radiating away from the Sun. That signal is normally the calling card of outgassing, but tight Spitzer limits on CO and CO2, plus the lack of dust, left almost no conventional exhaust to point to. Whatever was venting, if anything, must have been both efficient at pushing and nearly invisible at 4.5 micrometers, a constraint that has fueled years of modelling. What matters for the scoreboard is the diagnostic. Oumuamua showed that interstellar debris can be small, faint and non-conforming, forcing us to calibrate our techniques to read forces rather than just images. Then came the palette cleanser. 2I/Borisov arrived in 2019 looking gloriously normal. An obvious coma and tail, bright dust, classic emission bands. But normal turned out to mean comet, just not our average one. Radio and UV optical spectroscopy showed that Borisov's gas was rich in CO relative to water. In some analyses, CO rivaled or exceeded H, 2O in abundance, pushing it toward the cold outer disk flavour of comet chemistry. Later, high-resolution spectra stacked another surprise: neutral nickel and in solar system comets, iron atoms floating in the cold coma, proof that metals can leak into the gas phase far from any furnace. Put simply, Borisov taught us that interstellar comets can look familiar while whispering different chemistry. Now, watch how 3I Atlas rearranges the board again. Very early in its inbound arc, far beyond the water-friendly zone, JWST/NER spec peeled open the infrared and found a CO2-dominated coma, with spectral images showing a bright 4.26 micrometer hill and a sunward-leaning plume. At a heliocentric distance of about 3.32 astronomical units, the gas mix had CO2 clearly outpacing H2O with CO dust, and even water ice grains present but not driving the show. That's a different thermostat than we're used to. At these temperatures, dry ice physics can power the coma while water stays largely locked down. Because one telescope is a snapshot and two make a movie, Spherex stepped in with wide-field, multicolour maps that traced an extended CO2 halo out to hundreds of thousands of kilometres, big, bright, and persistent enough to rule out a one-off burp. With that context, the picture sharpens. 3I Atlas is CO2, lead at distances where many comets are quiet or just barely steaming, and its activity is strongly sunward asymmetric, the signature of dayside patches waking easily in low heat. That pushes its chemistry to a different corner of parameter space than either Oumuamua, no detectable volatiles, or Borisov, CO-rich, water-active. Discovery circumstances say something too. Oumuamua was caught late and fleeting, the arc was short, the photometry sparse, and the best we could do was squeeze physics out of precise astrometry and deep upper limits. Borisov benefited from longer, brighter coverage and became an all-instruments welcome campaign. 3I Atlas, spotted by the Atlas Chill Station and confirmed rapidly, is landing in the sweet spot, early enough for a coordinated onslaught from space and ground, bright enough for mapping, and compositionally off-script in a way that pays dividends. NASA's running notes even flag the basic geometry: a safe wide pass through the inner system with perihelion near the end of October 2025, just inside Mars's orbit. Ample time to watch its chemistry evolve. On the chemistry column of the scoreboard, the contrasts stack neatly. Oumuamua, no detected coma, tight limits on familiar volatiles, non-grav acceleration all the more puzzling in the absence of obvious gas. Borisov, abundant CO, a bright water-bearing coma, and even metal atoms turning up in the gas. 3I Atlas, CO2 in command at 3 plus AU, CO and H2O, present but not leading, a coma that leans toward the sun and inflates far from the nucleus. The overlaps matter as much as the differences. Borisov and 3I Atlas both tell us that outer disk volatiles CO and CO2 can dominate an interstellar comet's early activity but they split on which of those two carries the flag. The methods column is instructive as well. Oumuamua forced observers to treat the trajectory itself as data. The acceleration curve became the spectrum we didn't have. Borisov let us dust off the whole comet toolkit from ALMA to HST and prove that standard diagnostics work beyond our family. 3I Atlas is the first interstellar visitor to be caught by JWST and SPHEREX together, so we can map drivers CO, 2 versus H2O versus CO in space and time, rather than infer them from a single line or band. That multi-instrument coverage is how you separate what is present from what is in charge. If you like simple heuristics, organise them this way. Activity driver at approximately 3 astronomical units. Oumuamua, none seen. Borisov, CO strong with water active. 3I Atlas, CO2 strongest. Morphology. Oumuamua, point source. Borisov classic dusty coma and tail. 3I Atlas compact infrared core with a sunward CO2 fan and a very extended CO2 halo. Discoverability. Oumuamua, late, faint, fast. Borisov, bright and friendly to amateurs. 3I Atlas, early enough for the big guns, faint in the optical but loud in the infrared. Each row on that matrix is a reminder that interstellar isn't a type so much as a passport stamp. Chemistry and physics still tell the story, and they're not repeating themselves. And tucked in the margins are the meta lessons. Non-gravitational forces can be read cleanly if your astrometry is good enough. Thank you, Oumuamua. Carbon oxide-rich comae are not exotic one-offs. Thank you, Borisov. Carbon dioxide can dominate interstellar activity far from the Sun, and we can watch it directly with the spate-based spectroscopy and all-sky mapping. Thank you, 3I Atlas. The scoreboard keeps growing columns, dynamics, volatiles, metals, dust, because with each new arrival we get to write in a property we didn't know we needed to track. Imagine tracing a curve through space with a fingertip, a long fall-in from the direction of Sagittarius, a skim just inside Mars's orbit, and then the clean swing back out toward Jupiter in the dark. That's the flight plan of 3I Atlas. The path is hyperbolic, not a loop, but a one-way arc, so every observing window is a single shot. The calendar on the wall looks like this. Discovered July 1st, 2025, a Mars-side passage around October 3rd, 2025, at roughly 30 million kilometers. Perihelion near October 30, 2025 at about 1.4 astronomical units from the Sun, then lost in solar glare before reappearing for Earth-based telescopes in early December 2025 as it climbs back into the evening sky. After that, it slides past Jupiter in March 2026, already coasting for the exit ramp. Each date isn't just a milestone, it's a different chemistry lab, a different phase angle, a different chance to catch the coma changing in real time. The Mars chapter is a story in itself. When 3I Atlas passes the red planet on October 3rd, European and American orbiters plan to try for a look. ESA has publicly said Mars Express and the ExoMars Trace gas orbiter will be ready to attempt observations around closest approach, while NASA assets like MRO are on various if geometry cooperates watch lists. The distance, on the order of 30 million kilometers, means there won't be a postcard nucleus shot. You can still do science. Measure how bright the comet is from a vantage point away from the Sun-Earth line. Look for asymmetry in a sunward plume. Compare coma profiles from Mars's line of sight to what Hubble and ground observatories see from ours. Even a non-detection sets limits and pegs models. From Earth's perspective, the most frustrating part is that the comet gets the most active right when we can't see it. Geometry drags it behind the Sun in late October, so ground observers lose it just as the heating peaks. Multiple outlets have stressed the practical upshot. Enjoy the September window, then expect radio silence until early December, when it pops out again into a darker sky and cooler state. That is exactly why spacecraft coverage matters. The orbiters at Mars, Hubble, Webb, JWST, and SPHEREX don't care about your rooftop horizon. They can keep the movie running through conjunction, then hand the baton back to mountaintop telescopes when the comet returns to view. The instrument timeline already reads like a relay. Hubble locked a clean image on July 21, 2025, showing that soft teardrop coma wrapped around the nucleus and giving the first tight bounds on the core's size. Webb followed on August 6th with NEARSpec prying open the infrared to identify CO2, water, ice and gas, CO, dust and OCS, and, crucially, showing that the coma is CO2 dominated at 3.32 astronomical units with a sunward enhancement. SPHEREX took over in mid-August, mapping a vast extended CO2 halo hundreds of thousands of kilometres across and putting numbers on gas production rates and ice absorption. Those three vantage points, optical imaging for size and morphology, high-resolution infrared spectroscopy for chemistry, and all-sky near-IR mapping for spatial context, are what make this fly-through uniquely well characterised, even before the Mars segment begins. After perihelion, the arc doesn't end, it changes sign. 3i Atlas turns outbound, and the sunlight that once woke CO2 begins to fade. That's when you can watch species trade places as the driver of activity. Does water briefly surge as deeper layers vent, or does the coma stay carbon oxide-led even as the nucleus cools? The outward leg is also when the object's phase angles swing to values that favour dust-scattering studies from Earth, while Jupiter's neighbourhood in March 2026 gives outer planet missions a chance, if only a slim geometric one, to squeeze in additional measurements. NASA has already flagged a long list of assets that either observed or may try for a look, including Hubble, Webb, SPHEREX, solar observatories like SOHO, and even a handful of planetary missions keeping an eye on the sky between primary tasks. For planners, the geometry dictates tactics. Non-sidereal tracking to follow a moving point, short exposures to beat trailing stacked deep, UV optical at high resolution when you want to pick out narrow lines, 4.26 micrometers when you're chasing CO2 straight. If you're at the Mars, you point sunward to intercept that bright lobe Webb saw and measure whether the gas density falls off like a short-lived parent, fast photolysis near the nucleus, or a long-lived one, broad lazy halo. If you're on Earth in December, you watch whether the CO2/H2O ratio pivots, and whether any metal emissions hinted at by ground spectroscopists evolve with the fading of carbon oxide jets. Each angle answers a different question. Together they knit a single trajectory into a time-lapse of a foreign world losing its volatiles on our doorstep. Interstellar visitors are not just curios, they're control experiments for planet formation. In our own models, dust wants to drift inward and fragment before it grows. Getting from pebbles to kilometre-scale planetesimals runs into the metre-size barrier where dragon collisions beat you up. One elegant workaround is to import the big pieces, sweep up interstellar planetesimals that were built and then ejected in other systems, and let them seed a young disk with ready-made boulders. In that picture, an object like 3i Atlas is a representative of the seed population, the kind of body that, when captured by gas drag or gravitational focusing, can jumpstart growth from dust soup to solid cores. The idea is no longer armchair speculation. Capture models show that during the disk-building phase, a forming system can trap large numbers of metre to tens of metres interstellar objects, and even a few kilometre-class ones, depending on local gas density and streaming velocities. Once inside the disk, these seeds accrete fine dust rapidly, beating the inward drift clock and snowballing into larger planetesimals. In open clusters where stars are born close together and the background density of ejecta is higher, the capture rates go up by orders of magnitude, which maps neatly onto the observation that massive stars often host more and larger giant planets, The physics is simple. Bring your own boulder. Fresh Work presented this. September pushed the point with 3i Atlas as the mascot. Interstellar bodies can serve as seeds that short-circuit the bottlenecks in core accretion. If disks really are peppered with passers-by built elsewhere swept up here, then the diversity we see from Oumuamua to Borisov to 3i Atlas is not a curiosity. It's the menu of ingredients a baby star might inherit. In that view, a CO2 forward object isn't weird, it's a flavour, and capturing flavours at different radii could help explain why some systems lean toward gas giants while others stall at super-Earths. Chemistry is the lever that moves these arguments. Borisov already told us that some birthplaces bake comets with CO abundances, surpassing water inside 2 to 3 AU, evidence for cold formation zones and volatile rich layers. 3i Atlas goes a step sideways. CO2 dominates at 3.3 AU, sunward, and by a large factor, which is consistent with either formation near a CO2 ice line or surface layers processed by hard radiation in its natal system. If protoplanetary disks capture a mix of such bodies, the initial volatile budget of a young system could shift dramatically, with consequences for how quickly cores grow and how atmospheres assemble. The seed and capture picture doesn't require every disk to behave the same. In fact, it thrives on difference. The details matter right down to the atoms. If ground spectra continue to show metal emissions, especially if any nickel features correlate with CO2-like curves, that's a direct clue to surface chemistry that operates at low temperatures, the kind that would be active in outer disk regions where seeds would most likely form and be ejected. Pair that with SphereX, maps of an extended CO2 halo, and Webb's measurement of an 8:1 CO2/H2O mix inbound, and you have a compositional profile that a disk model can plug in. How sticky the dust is in that gas, how quickly a captured seed grows, whether it drifts or parks at a pressure bump, which side of a snow line it prefers to die or bloom on. The sky supplies the boundary conditions, the simulations do the rest. Even if no disk ever captured a twin of 3i Atlas, learning its volatile ratios, how its coma breathes with the sun, and which lines flicker as it warms, gives us a measured point in the distribution of solids other stars make. Feed in more points and the distribution stops being a guess. You start to see whether carbon oxide-heavy seeds are common, whether water-starved surfaces are a phase or a lineage, whether the ingredients for fast planet building are everywhere or rare enough to count on one hand while the object keeps sweeping past the sun, changing the light it gives off by the hour, turning geometry into chemistry into the kind of numbers disk models can't ignore. Start by watching the light, not the pictures. If CO2 keeps running the show, its 4.26 micrometer band should pulse as the sun angle changes, fast near local noon on the nucleus and softer toward its night side. JWST has already caught a CO2-led coma. Now the game is to see whether that dominance holds as the heliocentric distance shrinks to approximately 1.4 astronomical units and then grows again. A pivot toward water would show up first as a rising 2.7 micrometer H2O band and a thickening OI 6,300 angstrom line in optical spectra. If the pivot never comes, then 3i Atlas is telling us its near-surface plumbing is carbon oxide through and through. Either way, the light curve of that CO2 line, mapped against distance and rotation, will be the metronome of the coma. Pair that with the metals. VLT work has already flagged neutral nickel lines turning on early, with iron stubbornly faint or absent at similar distances. If nickel really rides along with CO/CO, to chemistry, for example via photolysis of a fragile carbonyl parent, then the intensity of Ni lines should correlate with CO2 brightness. Watch for two specific signatures. 1. A steep near-nucleus nickel peak, short parent lifetime, and 2. Growth of Phi. I only when the comet gets warmer and deeper layers or different carriers engage. A divergence, knee up while Phi stays flat, keeps the low temperature chemistry picture alive. A late-onset Cepheid would hint that the thermostat finally clicked to a new setting, mapping matters as much as rates. Sphere X has already shown an extended CO2 halo, hundreds of thousands of kilometers across. Revisiting that map as 3i Atlas rotates can tell us whether the gas is jetty and short-lived or slow and diffuse. Cross-register those wide maps with high-resolution slits that rake across the sunward lobe. If nickel truly hugs the CO2 jets, Ni should spike along the same filaments that Webb, SPHEREX isolate in the infrared. Dust polarimetry layered on top will reveal grain size changes driven by a CO2 wind strong enough to loft bigger particles than water could at the same distance. The calendar is a science instrument too. The Marsside passage around 3rd October 2025 offers a non-Earth vantage. Mars Express and the Trace Gas Orbiter have a narrow window to sample the coma from off the Sun-Earth line and test whether that bright sunward CO2 apron looks different in phase from what we see here. Then comes perihelion near 30th October 2025 at roughly 1.4 astronomical units, ironically when ground observers lose it in the glare, followed by a December reappearance as activity wanes and the chemistry either trades places or digs in. Farther out, the mid-March 2026 pass near Jupiter is a slim chance for outer-planet assets to grab supplemental views, even if deep flyby campaigns aren't feasible. Each date is less a circled day than a different physics regime. Low energy desorption now, deeper heating later, then the long cool down. Use the geometry to solve the nucleus. Hubble's early optical imaging gave a clean teardrop coma and first radius bounds. Repeating that imaging post-perihelion, when the gas subsides, tightens the size estimate because the dust veil thins. Combine that with rotational light curves from fast cadence photometry to fish out the spin period. If jets wobble with a regular beat and spectral lines breathe on that same beat, you've tagged the rotation and can map active longitudes. The moment the coma turns transparent enough, look for a fresh upper limit, or detection, on the nucleus and a refined albedo. All of those feed back into mass/torque estimates when you model any non-gravitational forces. Keep the wavelengths talking to each other. A practical playbook looks like this. A. From space, ride 4.26 micrometers for CO2 and track H2O/CO companions. B. From large ground telescopes, use high-resolution optical for NEI, FEI, CN, and OI. C. Stitch in near-IR reflectance to monitor water ice grain features near 2.0 micrometers. And D. Add wide-field mapping, Sphere X style, to follow how far the gas spreads and how fast it thins. If nickel continues to soar with CO2 while CN lags, the surface story is the low-temperature release rules. If CN surges and iron finally joins, you've crossed a threshold into warmer, more familiar comet chemistry. The value isn't in one instrument, it's in the braid. The what next also includes negative space, what you don't see. If CO stays relatively modest compared to CO2 across the inbound and outbound legs, that's a direct clue to the ice inventory and how heat penetrates the crust. If CO starts catching up as the comet warms, that shifts the inferred depth of the CO reservoir. If V continues to hide while Ni sings, even post-perihelion, that leans harder towards selective carriers or redox-specific micromineralogy. And if nothing pivots, CO2 rules throughout, you've met a surface that never lets water set the terms until it's too late. A rare but telling end member for models of where and how such bodies form. Strategy for the December return is simple and ruthless. Short, non-sidereal exposures stacked deep to track a fainter target, slits aligned with the known sunward axis to squeeze out residual CO2, a nightly cadence to watch ratios evolve on timescales of hours to days. If the nickel-CO2 correlation holds, you should see NEI fade roughly in step with the 4.26 micrometer band. Any decoupling would be its own story, pointing to different parent lifetimes or a changing jet geometry as illumination slides across the nucleus. Meanwhile, small aperture photometry contributes by pinning dust colour slopes and phase angle effects that large telescopes don't have time to chase. Nothing about this visitor is a repeat. Oumuamua made us read forces without lines. Borisov gave us a normal comet with an outer disk accent. 3i Atlas has handed us CO2 supremacy at 3 plus AU plus a metal signature with a personality. What to watch next is exactly that personality evolving under sunlight. Which species lead, which follow, which never show. Those choices, written in narrow lines and in infrared hills, are the breadcrumbs back to a home star we'll never see, and picture a speck from another star system drifting through the dark and an entire planet's worth of instruments swiveling to greet it. That is the scale of the moment. We have a third interstellar messenger, a body with a CO2 breath and a nickel voice, swinging past our sun on an open curve, and we're catching it from every angle we've learned to use. The far infrared glow that tells us which ices wake first. The razor-thin optical line is seduced to betray atoms, shaken loose at surprisingly low energies. The teardrop coma invisible light that hints at the nucleus hiding inside. The off-axis views from Mars that let us see the same plume from the side. None of this existed when the first one surprised us 8 years ago. Now it does, and it's all focused on the same small stranger. If we've learned anything from Oumuamua and Borisov, it's that interstellar isn't a single kind of thing. It's a passport stamp, not a species. 3i Atlas isn't here to fit our rules. It's here to show us a set we didn't know to write down. Maybe its surface was baked by the radiation, in a different kind of nursery. Maybe it grew where dry ice was easy to make and hard to melt. Maybe metals on its skin learned a trick that frees nickel earlier and easier than iron. Each hypothesis has a line in the spectrum to prove or kill it, and every line we record becomes part of a new cookbook for how worlds start in places we will never visit. The romance of it is quiet and technical. Rotating slits to match a faint fan of gas, subtracting Earth's own water from a spectrum so that alien water has a chance to speak, counting photons so few you could hold them in a thought, and turning them into numbers big enough to argue about in papers. The thrill is not fireworks, it's fit residuals shrinking, uncertainties collapsing, two instruments agreeing within error bars that the thing you suspect is real. You don't get many visitors like this. You make the most of them by listening hard. And when it slips back into the dark, it won't take the data with it. The maps of CO2, the time series of nickel, the shape of the dust, the way the coma inhales and exhales as sunlight passes over a spinning foreign crust, those will stay. They'll bend models of disks and snow lines, of capture and seeding, of how often a young system might inherit someone else's rubble and build a planet faster than it otherwise could. That's the point of paying attention to a single faint blur, to enlarge the set of ways a world can begin, and to be ready for the next dot that creeps across the starfield and asks, without words, whether we'll notice it in time.